Section 4.10, Antiderivatives. In this unit, we're going to discuss the second famous problem that helped motivate the development of calculus, that being area. Before diving into area, we need to talk about antiderivatives. Finding an antiderivative is the reverse process of differentiation. A function capital F is an antiderivative of a function f if capital F prime of x equals f of x for all x in the domain of f. In other words, to find the antiderivative of a function f, we're trying to find a function whose derivative is equal to f itself. To help us understand this definition, consider f1, which equals x squared over 2, f2, which equals x squared over 2 plus 1, and f3, which equals x squared over 2 plus pi. All three of these functions have a derivative of x. f1, f2, and f3 are all antiderivatives of f of x, which equals x. It turns out because of the derivative of a constant being 0, a function will have infinitely many antiderivatives. For this reason, we have the general form of an antiderivative. That being, let capital F be an antiderivative of f over an interval I. Then, for each constant c, the function capital F of x plus c will be an antiderivative of f over I. This is because when we take the derivative of a function, we do so one term at a time. If I take the derivative of capital F of x plus c, the derivative of capital F by definition would be little f, while the derivative of c would be 0. So by definition, f of x plus c would also be an antiderivative of f of x. So if I know one antiderivative, I can come up with infinitely many more just by adding a constant. But the question then becomes, what do all antiderivatives look like? If g is an antiderivative of f over I, then there's a constant c for which g of x equals f of x plus c over I. In other words, if I have two different antiderivatives of f of x, their difference would just be a constant. The reason why this statement is true is not necessarily intuitive, but is a result of the mean value theorem. We can let h of x equal the difference of our two antiderivatives, g of x and f of x. In which case, h prime of x, because g of x and f of x are both antiderivatives, we would get 0, since the derivative of g of x and f of x would both be equal to little f of x. As a result of the mean value theorem, since h of x would be differentiable over our interval I, there would be a c inside of the interval ab such that h prime of c would equal h of a minus h of b all over a minus b. But we know h prime of c is always 0, which by multiplying over ab and adding over h of b, we get that h of a equals h of b. So this result tells us that h of x actually equals some constant c the entire time. And if we add over the f of x, that would give us that g of x equals f of x plus c. This result is very powerful. The most general form of our antiderivative f over some interval I is always going to be f of x plus c. Once when you find one antiderivative, you now know all antiderivatives by adding various constants to the original antiderivative that we found. The term that's often associated with antiderivatives is indefinite integrals. We're going to let f be a function. The indefinite integral of f, which is going to be denoted here with this elongated s-looking symbol, f of x dx, represents the general antiderivative of a function f. If we know that capital F is an antiderivative of f, then the indefinite integral of f of x with respect to x is equal to capital F of x plus c. So the phrase indefinite integrals is used to represent the family of antiderivatives of a particular function. Oftentimes, we will use the phrase indefinite integrals and antiderivatives interchangeably. As for the names of the various parts of this notation, f of x is referred to as the integrand, and the variable x is referred to as the variable of integration. Just like with derivatives, we do want to know what the indefinite integrals of a variety of commonly used functions will be. Here, we have a list of 10 basic rules for a variety of functions we often see. First, the integral of a constant. The integral of k with respect to x will equal kx plus c. One thing to note is you're going to see plus c at the end of every integration rule. That is because the plus c is needed to represent every possible antiderivative. It is very important that you remember to put the plus c, since when we're finding an indefinite integral, we are looking for all of the possible antiderivatives of the integrand, not just one specific antiderivative. As for why this rule holds true, if we differentiate kx plus c, we are left with k, which is our integrand. And this is how you can verify that all antiderivative rules are correct. If we take the derivative of what we're claiming to be the antiderivative of our function, and we get that integrand, then we have the correct antiderivative. The next two rules are how we handle power functions. The first is what we call the power rule. The integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus our constant. This is true because if we use the power rule of derivatives to differentiate our antiderivative, the derivative version of power rule has us bring down the exponent and subtract 1 from the exponent. The n plus 1's cancel, and n plus 1 minus 1 would just be n. So the derivative of x to the n plus 1 over n plus 1 is x to the n. So the antiderivative of x to the n is x to the n plus 1 over n plus 1. One thing that is very important, though, the power rule for integration only applies for powers that are not equal to -1. If we want to integrate x to the -1 dx, that is the same as integrating 1 over x. This requires a different rule. From our basic derivative rules, we know that the derivative of the natural log of x is equal to 1 over x. So we could say that the antiderivative of 1 over x with respect to x would be the natural log of x. However, 1 over x has a much larger domain. The domain of 1 over x is all real numbers except for 0, while the natural log of x has a domain of only positive numbers. One rule that can be verified through the difference quotient is that the derivative of the absolute value of x is equal to the absolute value of x over x. Now, if I look at the natural log of the absolute value of x, since the absolute value makes negative numbers positive, then the domain of the natural log of the absolute value of x would be all real numbers except for 0, just like the 1 over x. Furthermore, thanks to chain rule, we also get that the derivative of the natural log of the absolute value of x is 1 over x. So for that reason, the antiderivative of x to the -1, or the antiderivative of 1 over x, will be equal to the natural log of the absolute value of x plus c. That way, we have a bigger domain to look at. As for the other rules, the antiderivative of e to the x is e to the x plus c. The antiderivative of cosine x with respect to x is sine x plus c. And the antiderivative of sine x is negative cosine x. Keep in mind, always remember to put the plus c at the end. These three rules are pretty straightforward to verify. If we just take the derivative of e to the x sine x and negative cosine x, we do get the integrand we're finding the antiderivative of. The next four are a little obscure at first and may seem a little bit more difficult to memorize, but you do want to get very familiar with them. These rules are: the antiderivative of secant squared x is tangent x. The antiderivative of cosecant x cotangent x is negative cosecant x. The antiderivative of secant x tangent x is secant x. And the antiderivative of cosecant squared x is negative cotangent x. And again, do not forget the plus c. All four of these rules are just based off of the derivative rules for tangent, cosecant, secant, and cotangent. Notice how we do not have the antiderivative of tangent, secant, cosecant, or cotangent on this list. Their antiderivatives are a little bit harder to derive. Oftentimes, those are introduced in Calculus 2 because they do require special techniques to help us integrate. But these are 10 basic indefinite integral rules that we should remember and we'll see very frequently throughout this course. Just like with derivatives and limits, we do need rules for finding the indefinite integral of a combination of various functions. The two rules we're going to discuss are the constant multiplier rule and the sum and difference rule. The constant multiplier rule tells us if we're finding the integral of k f of x dx, then that'll be equal to k times the integral of f of x dx. In other words, when we're finding the antiderivative of a function, we can kick constant multipliers outside of the integral. The sum and difference formula states that if we're finding the antiderivative of f of x plus or minus g of x, that equals the antiderivative of f of x plus or minus the antiderivative of g of x. So the antiderivative of a sum and difference is equal to the sum and difference of the antiderivatives. As for the constant of integration that we've seen in the past basic rules, after we've applied the rules and we have found the antiderivative of what's left, we just put a plus c at the very end of the problem. The reason being, suppose that the antiderivative of f of x is capital F of x. Now, usually whenever we replace something with an expression, we do put parentheses. So the antiderivative of k f of x dx would be k times the capital F of x plus a constant, which we're going to call c1. Distribute into k and we get k f of x plus kc1. However, the kc1 is already a constant. Because the kc1 would be a constant anyway, I can avoid having to worry about distributing. And if I already know that capital F of x is an antiderivative of little f of x, then I can just simply state that my answer is k times f of x plus a constant c and not have to worry about the distributive property. The same thing goes for the sum and difference rules. If capital F of x and capital G of x were the antiderivatives of little f and little g respectively, then when I find the antiderivatives of little f and little g individually, I would get capital F of x plus c1 and capital G of x plus c2, where c1 and c2 would be the respective constants of integration for the two functions. If I rearrange my terms with the plus or minus, I would get that my antiderivative would be f of x plus or minus g of x plus c1 plus or minus c2. But just like k c1 was a constant, c1 plus or minus c2 was also just a constant. Because the constants of integration for each individual antiderivative would collect into another constant, when I'm applying the sum and difference formula, I can find the antiderivatives individually and then just add a single constant of integration at the end. And I won't have to worry about any manipulations, playing with constants, or absorbing constants into a new constant. The general rule of thumb is once when you've found all your antiderivatives after breaking up your integrand using the constant multiplier rule and sum and difference formulas, you just put a plus c at the very end of it to represent the general form of the antiderivatives. The constant multiplier rule and the sum and difference rules are exactly the same as what we've seen so far for limits and derivatives. With derivatives, we saw a product rule, quotient rule, and chain rule. Unfortunately, there is not a product rule, quotient rule, nor chain rule for antiderivatives. This is because there are several different ways to write and simplify a function. One of the big issues with integration is it relies on a lot of several different techniques that can be applied in different situations. We'll learn one of those techniques later in this unit called substitution. If you take Calculus 2, you'll learn several more integration techniques that can be used in specific situations. Now we're going to evaluate the following indefinite intervals. We'll start by finding the integral of 15 with respect to x. Since 15 is a constant function, then according to the list of basic integral rules, an antiderivative of 15 would be 15x. Once when we figure out the antiderivative, remember to put plus c at the end. So the indefinite integral of 15 would be 15x plus c. Next, negative 5x dx. Here, negative 5x is not a constant function, but negative 5 is a constant multiplier. So we can kick the negative 5 out of our integral. Now we have to find the antiderivative of x. If we treat x as x to the first power, we can apply the power rule for integration. To apply the power rule of integration, we add 1 to the exponent, and we divide by that new exponent. Since we just finished finding an antiderivative, we should put a plus c now. Once when all integrals are gone, that's when we put a plus c. We can do a little bit of simplifying. 1 plus 1 is 2, and negative 5 times x squared over 2 can be written as negative 5x squared over 2. And remember that plus c at the end. So the indefinite integral of negative 5x is negative 5x squared over 2 plus c. Next, we'll evaluate the indefinite integral of 5x cubed with respect to x. Just like in the problem above, we can move 5 out of the integral since it's a constant multiplier. Now we can evaluate using power rule since x cubed is a power function. So we'll add 1 to our exponent and divide by the exponent, giving us 5 times x to the 3 plus 1 over 3 plus 1. And since we evaluate our integral, we'll include the plus c. Now we can do a little cleanup. 3 plus 1 is 4, and we get that the indefinite integral of 5x cubed is 5x to the 4th over 4 plus c. Next, we're going to evaluate the integral of 5 4th root of x plus 1 over x squared. Just like with derivative problems, we don't want to work with radicals. So we'll rewrite the 4th root of x as x to the 1/4. Now, as for the 1 over x squared, we can rewrite that with a negative power. 1 over x squared is the same as x to the negative second. We do have to be a little careful with negative exponents. Remember, power rule for integration only works for exponents that are not negative 1. Since our power right now is negative 2, everything is fine. From there, we can use the sum and difference rule, and we can split up our integral to the integral of 5x to the 1 over 4 plus the integral of x to the negative second. For the first integral, we can kick out the constant multiplier of 5. Now, x to the 1/4 and x to the negative second are both power functions that we can apply the power rule to, since neither exponent is negative 1. And the antiderivative of x to the 1/4 would be x to the 1/4 plus 1 over 1/4 plus 1, while the antiderivative of x to the negative second is x to the negative second plus 1 over negative 2 plus 1. We can clean up by doing the addition. Then we can clean up the denominators. For the division of 5 over 4, that is the same as multiplying by 4 over 5. As for the division of negative 1, that would change the plus to a negative. And then multiply the 5 and the 4/5, and we get that the antiderivative of 5 times the 4th root of x plus 1 over x squared is 4x to the 5 over 4 minus x to the negative 1 plus c. In this example, we're going to have to really be careful with our restriction on the power rule. We're going to find the indefinite integral of 3 over x plus 2 over x squared. If we were to take the same approach as the other problem, we can rewrite our 3 over x and 2 over x squared so that way we have negative powers. And our integrand becomes 3x to the negative first plus 2x to the negative second. The x to the negative second is perfectly fine for power rule. However, x to the negative first is a problem. We cannot use power rule when our exponent is negative 1. In fact, we have to use a different rule altogether. Instead of looking at it as x to the negative 1, let's bring it back and write it as 3 times 1 over x instead. Now we can apply a combination of the sum rule, and when we do, we have 3 times the indefinite integral of 1 over x plus 2 times the indefinite integral of x to the negative second. As we discussed before, we cannot apply power rule to 1 over x. But if we look at our table of rules, there's a special integral for 1 over x. The integral for 1 over x is the natural log of the absolute value of x. As for the x to the negative second, because that's a power that's not negative 1, we can apply the power rule. And our antiderivative of x to the negative second would be x to the negative 2 plus 1 over negative 2 plus 1. Now we can do a little cleanup, and our indefinite integral of 3 over x plus 2 over x squared will be 3 natural log of the absolute value of x minus 2 times x to the negative first plus our constant c. Now we're going to evaluate the indefinite integral of negative 6 e to the x plus cosecant squared x. Just like in the previous examples, we can use a combination of the sum and difference and constant multiplier rules, and our integral becomes negative 6 times the integral of e to the x plus the integral of cosecant squared x. The antiderivative of e to the x is e to the x. In general, the antiderivatives of trig functions can be a little bit difficult. We're going to talk about another example later on showing how it can be difficult, but it's very important that you pay very close attention to the basic rules we have. If you look back at the list of basic rules, we do see one explicitly written for cosecant of squared x. The antiderivative of cosecant squared x is negative cotangent x. You want to make sure you really know those lists of basic rules. When you learn more techniques of integration, you may be tempted to use an incorrect technique to integrate the cosecant squared x. However, if you know the list, you'll know that this is what we would consider a basic integral. There's nothing left for us to clean up, so the antiderivative of negative 6 e to the x plus cosecant squared x is negative 6 e to the x minus cotangent x plus a constant c. In general, integration is a lot harder than differentiation. When finding the derivative of a function, we can boil them down to a combination of basic rules, constant multiplier rules, sum difference, product, quotient, and chain rules. However, due to the lack of a product rule, quotient rule, or chain rule for integration, we oftentimes have to be a lot more creative when it comes to integrating. And here we're going to highlight a few examples where we do have to be a little bit more creative. Let's start with the antiderivative of tangent squared x. If we refer back to the list of basic rules, tangent squared x is not on them. So we have to figure out how to rewrite the tangent squared x so that way we can find the antiderivative. Now, if we think very carefully, tangent squared x is related to one of the functions on our list. If you recall from pre-calculus, 1 plus tangent squared x equals secant squared x. Secant squared x is on our list. If we subtract over the 1, we get that tangent squared x equals secant squared x minus 1. Secant squared x is on our list of basic rules, and 1 is constant, which we can integrate. So we can rewrite our integrand and turn our integral of tangent squared x to the integral of secant squared x minus 1. From there, we can apply the sum and difference rules, then integrate each integral. The antiderivative of secant squared x is tangent x. The antiderivative of 1 is x. So the antiderivative of tangent squared x is tangent x minus x plus c. Next, we're going to integrate the square root of x cubed plus 4 with respect to x. As stated on an earlier slide, we do not have a product rule, a quotient rule, or a chain rule. So when a situation with multiplication arises, we have to hope that there's a technique that's going to allow us to integrate, or we can be able to rewrite our integrand so that way we can get rid of the multiplication. Taking a look at this problem here, we can rewrite the square root of x as x to the 1/2. Then we can distribute the x to the 1/2 into the x cubed plus 4. And we get x to the 7/2 plus 4x to the 1/2. Then from here, we can integrate like in the past examples. And after applying the power rule and simplifying, we get that our antiderivative is 2x to the 9/2/9 plus 2 times x to the 3/2/3 plus our constant c. Next, we're going to evaluate the indefinite integral of x squared plus x plus 1 over x. As stated before, there is no quotient rule for integration. So we have to rewrite our integrand so that way we can apply our properties. In situations like this where I'm dividing by a single termed expression, we can use fraction decomposition to help us. Recall that when we add fractions, we always need a common denominator. So if we add a over b plus c over b, that is equal to a plus c over b. Most of the time, we use this relationship when we add fractions. However, we can always reverse this and use this little rule to rewrite our integrand as the sum of several fractions. So x squared plus x plus 1 all over x can be rewritten as x squared over x plus x over x plus 1 over x. Simplify where we can, and our integrand becomes x plus 1 plus 1 over x, and now we can integrate each term one term at a time. The antiderivative of x, which we've seen before, would be x squared over 2. The antiderivative of 1 is 1x or just x, and the 1 over x, its antiderivative is the natural log of the absolute value of x, and then we put our plus c at the end. What makes integration so tough is that there are so many different techniques. Other than applying basic rules, we'll learn one other technique later on this unit called substitution. If you take Calculus 2, you'll learn several other techniques for integration.